to THERMO KK, Sem 2, 21-22. So this test covers chapter 6 and 11. So chapter 6, the main idea of chapter 6 is just the residual properties, and chapter 11 is the fugacity. So basically what chapter 6 is about is, before this, when we go through chapter 3 and 4, when we calculate thermodynamic properties for a system, such as the enthalpy or the entropy, we are only considering the fact that the whole system is ideal, right? Ideal gas or ideal solution. But in general, it's ideal gas. But when we go into chapter 6, it starts to take real gas into account, real properties into account. So what residual properties talk about is the difference between ideal property and real property. So for example, when you calculate a system, when we consider real properties, we want to know how much our actual enthalpy deviates from the ideal enthalpy. That's just the rough idea, because I don't really have time to go through into details, but that's just it. So any formula that we have in chapter 6 is just an expansion from chapter 3. There's a long derivation, but yeah, what really is really important is just this one and this one: generalized property correlation, and also generalized correlation for second virial coefficient. So you guys want to pay attention to what the question wants. Sometimes the question wants generalized property correlation or Lee-Kessler. This is considered Lee-Kessler, if you guys still remember Lee-Kessler. Actually, Lee-Kessler has a lot of derivations, but for chapter 6, it's just this one that we are really concerned about. And for second virial coefficient, it's just this one, these long ass equations. So let's go through question first. The first question: propylene gas is compressed from an initial state of 400K and 5 bar, blah blah blah, 400K and 5 bar to final state of 550K and 20 bar. Estimate the enthalpy and the entropy. So when I see this question, so when I go through this question, what is really important is you want to draw the what do you call this, the process path. Yeah, the process path. So first, since the question doesn't state whether the initial state is ideal or real, so we always have to assume that it starts with real gas. Alright, unless the question states that, oh, maybe the question wants you to set the initial state as ideal, then you have to set it as ideal. But since it doesn't state that, we have to assume it is real gas. So first state is real gas, and then if you want to change the temperature to 550K and 20 bar, we first have to change it to ideal, because when we want to use this table, the A, B, C, D table, I forgot what is it called, the heat capacity table, the reference point is that the gas is ideal, so we have to change it to ideal gas first. So when we want to change it to ideal gas from real gas, we have to make it we have to take HR and SR. So why is it negative here? Because we know that for any thermodynamic properties, any thermodynamic properties in general is let me see, am I correct? Yeah. Right. So when we want to change it to ideal gas, it's gonna become, sorry, I left the residual here. So when we want to change it into ideal gas, it's gonna be, hold on, yeah. So your residual will be in negative coefficient, so that's why it's negative here. So you really have to pay attention to that, the negative sign and the positive sign. Yeah. And then you change it to ideal gas. The states are still the same, because we are only changing the state from real to ideal. Next, we are increasing the temperature from 400K to 550K. So this one we can just use the CPDT, which is this formula HIG equals to R T naught T CPDT. Yeah. And SR and SIG, you have that formula is this one, this formula here, T naught to T CPIG dt over T minus R ln P over P0 over P naught. So let's just go through my answers here. So first step is finding the residual properties for enthalpy 1 and entropy 1. So just basically this is just using the formula and just applying it back. So we know that the initial state, so yeah, you have to break down into two states, first the initial and the final. So initial state is this one and the final state is this one. So it's really important for you to like separate your reduced pressure and reduced temperature into different columns, so that you don't use the wrong information, you don't use the wrong value to find the reduced pressure and temperature. Yeah, and then so basically from then onwards it's just matter of substituting values into these equations here. Yeah, so it's the same thing honestly. For residual enthalpy and residual entropy, is this the same thing as ideal gases, ideal enthalpy and ideal entropy. It's just the matter of understanding how the process path works. Other than that, I think you guys are smart enough to just plugging in values into the equations. Yeah, and also just make sure you guys pay attention to the positive and negative sign, because here after you find all these residual second residual property and the first residual property and the ideal properties, you have to plug in back into the enthalpy, because the end goal is to find this delta H and delta S. So if we look at this process path here, we know that delta H is equals to negative delta H1R plus delta HIG plus delta H2R. So there's a negative sign here, and you just have to change your sign here because it's negative, but you want a negative value of that residual enthalpy. So you just have to pay attention to changes of signs, honestly. Other than that, I think yeah, it's pretty straightforward. It's just that you just have to pay attention to what formula you want to use, because here they said to use the generalized second virial coefficient, so that's why I'm using this one. But if they insist on using generalized correlation, let me see if I have an example question of them using that. Second virial, this is second virial too. Anyways, I can't seem to find any papers that demands a generalized property correlation, but this one, the keyword is Lee Kessler. Say they want you to find the enthalpy H and delta enthalpy and delta entropy, and they want you to use Lee Kessler, then sure, use this instead of this long formula. Yeah, SR1 and R you can find in table D5 to D12, and same goes to HR not RTC and HR1 RTC. You can find it in this table D5 to D12. Other than that, it's just a matter of knowing which formula you want to apply. But yeah, so this is just familiar. This is something that you are familiar with when you've gone through test 1, because this is just chapter 3, because this is ideal. So yeah, just CPDT ideal gases. Same goes for entropy. Only that thing that the one is new is just residual properties. Yeah, and that I feel like